there are two things I want to show now. One is how you can simulate the refocused INEPT and add a little bit of phase cycling, and then how you can detect two-spin order, the creation of IXSZ term. So let's start with refocused INEPT. So refocused INEPT will give. I just took this one because I could find a phase cycling that is easy to apply, and it will give a nice result. So we have two. We just add one echo here, so it will be very short to just add this in our pulse sequence. And then here I have written the two phase cycle. So the first one is along X, an acquisition along X, and then the second one is minus X, minus X. So let's have a look at this. I'm going to copy everything I did up to now for the INEPT. And this will be the refocused INEPT. So what does change here? What I have to do is after, if we go back here, we were detecting row 5. Here I have to do, again, free evolution during tau. So I copy this bit. This becomes row 6. Then I have to apply a pi pulse on both spins, the same as here. So I can simply copy this step. Yes. And after the pi pulse, again, I have to wait to do the free evolution during tau. Okay, let's verify the numbers. This was 5, 6, 7, 8, so I have all my steps. And now this is row 8 that I'm going to propagate. So I'm going to make a loop where I put my two signals in a different vector. So this will all go in a loop. So I'm going to move this outside of where the loop will be. Yeah. Up. This goes in the beginning before we start the loop. And here will be the loop. So here I have used index K. So now I'm going to use J. And there are two steps in the phase cycling, 1 and 2. And I move all this into the loop. Where's my loop? Here. For clarity. Oops. I write it like this. I move it on the right so that it's clearer, the hierarchy between the loops. This I don't need anymore. So this is the loop for each step of the phase cycling. We're going to go through the loop, and I want to define. Now this is no longer the right size. So there are two ways I can do this. Either instead of doing I can have this vector the same one as before, and here I will sum in the same vector, but I want to show you the result of phase cycling 1, and then phase cycling 2, and then the sum of them. So what I will do is here I make a matrix with 2 columns of and n rows. So this means that I simply add here J, meaning that when I propagate in the very end here, For phase cycling 1, this will go in the first column, and phase cycling 2, it will go in the second column. Here, now row K, the initialization of this iteration, I have to start with this one, row 8. And all I miss now is to define the phases. So there are many ways I could do this. I think it's nice to do it slightly like topspin. I'm going to define here pH, I call it list. So in topspin, 0 and 2 would mean that I'm posting along x, and 2 would be along minus x. And this would be the same. I'm going to define second one. Maybe the first part of the tutorial went quite fast. So I'm going to show you a way that is quite complete. Of course, it's a very simple case, so we could just write it manually. But I'm going to show you a way that is very, very clean. Well, let's call it 31. It's how it is usually called in topspin. So why did I have one phase cycling for here, one for here, and all the other pulses remain the same? So the first pulse has to be phase cycled. So here, and one way I can write this is this one. Explain in a second what I'm doing. So this is maybe too complicated, I don't know, but at least it works. When let's separate this a little bit. Ix, if this is 0, then it's cosine of 0, which is 1, so it's purely Ix. And 0 here means that the sign is 0, so it's no Iy. When this is 1, this is now cosine of pi over 2, so it's none of Ix, and it's fully Iy. And when this is 2, then this is cosine of pi, so it is minus 1, so it's minus 1 Ix. So this is a really complete way to write a phase cycling. That I define it in this way because it allows us to make something that is very close from what topspin does. And we have to do the same thing for detection. I'm going to create it outside because it's a bit heavy otherwise. So this will be detection along X, detection along Y. I'll just copy this. This phase is pH 31. So what I have created is sort of operators that will be used for detection. One for X, one for Y, and I just make these operators turn. So let's check when this is equals to 0, we have cosine of 0, so we have Ix, and we have Iy. And then when this is 2, as it will be at some point, we'll have cosine of pi over 2 times 2 will be cosine of pi, so it will be minus 1 as we wanted. So I think it is right. Is it clear? Do you have questions? No. Okay, so what I miss now is just plotting the signals. The function I've created, signal 1D, is not meant to have this matrix with two vectors. So what I want to do is to plot them separately. So this syntax tells me that I'm taking all the rows of column and column 1. It will plot the first one. We'll write it here. So as signal with phase 1. And now the same with phase 2, which is the second column. And now I will plot W. I will plot both of them on the same. And also, in the end, what we really want is to have the average to compare. There's a high chance that I have a mistake somewhere, especially in the phase. Let's have a look. So I run the code. What did I do? So first I should have real here. That's the warning that I got. So why do I get this? I must have made a mistake. I wanted to have certain C. So my problem now is that I see the two signals while I expected to have only one. I'm acquiring using IX and IY. Oh yes, detection is along S. If detection is along the carbon. This is the reason why I have this problem, I believe. Yeah. So I just have to change the phase. The phase is no longer this one. I guess 0 should work. It would be pi. Okay. Now let's zoom on this. No, they just apparently there's a mistake. So before I comment it, I'm going to repair this mistake. I wanted to add here divided by 2. So but I want to have phase 1, phase 2, and the average. I can plot it. What do we see here? You see the first phase is the blue one with this higher, this asymmetric pattern, and in the red one is the opposite pattern. And when we take the average of the two phases, we get this normal looking doublet. So probably what would now be cool is to add on the same plot the propagation of add the plot without the INEPT. So we can just copy what I did. Where was it? Here. So it's even easier than this. So let's have a look. It's I create a new vector st. The pulse along x. I take row 0, and then I propagate it in the same way as earlier. I think this is what I need. Oops. So now I create this one, no inept. Just want to have a look at the spectrum to be sure it is right. So I plot it, run the code. Okay. Just need to change the face. Yes, this is what I wanted. So now doing this, I saved in here. This is the signal without doing any INEPT, and I'm going to plot it on the same graph here. And this way you can really see the effect of the INEPT. We started with an intensity. Maybe I'm going to normalize. This will be interesting to show you how to do this also. I'm going to normalize the spectra by the intensity of this one, so that we see that we should have a 0.25 here if there's 1 here. And I'm just going to add some zero filling to have something cleaner. So I'm putting 16 times more points. Yeah, and now I'm going to calculate the MAC. M will be the maximum of this signal. So the function max in MATLAB, when you have a vector, it gives you the highest number in the vector. So I simply divide everything by this number. Oops. Now if I plot, so this is 1, and as you see, it's this is related to the ratio of the gamma of the proton and the carbon. So this is approximately 0.25. And if we just to see, as we did earlier, we can just have a look what would happen with an even lower gamma like a nitrogen 15. So just run the code, assuming it's nitrogen 15 now. And if I plot, I don't know why the phase has changed for some reason, but
because the gamma of nitrogen is negative.
Nice one. So I'm going to fix it very brutally by doing this. So in this case, it's approximately 0.1, which is related to the ratio of the gamma. I'm going to put it back to carbon, which was just for comparison. Okay, do you have any questions on this phase cycling thing? So the last thing I wanted to show today is we have seen this pulse sequence, and what I haven't commented is how it works. Really, if you look at the product operator, and you may know that you transfer the magnetization from one spin to the other one by using a term in a density matrix, which is it's 2-spin order. It's IX SZ and IY SZ, or the opposite. And it's interesting to track the creation of this term along the pulse sequence. And to do this, I want to introduce. I have already used extensively this product of the density operator with another operator and taking the trace, what we call the Leuven bracket. This formula, I use it all the time. I just want to add another tool to this. So when you can decompose the density matrix as a sum of using a basis, and typically we have seen last week that a spin in the alpha state, you can decompose it as the sum of the identity matrix and IZ. This is for a single spin system. And then we have seen for, I took another example from last week, a 2-spin system. if spin 1 has polarization 1 and spin 2 has polarization 2, you see this sum of operators that give the density matrix. You have the identity operator divided by 4, and then you have IZ for spin 1, I1Z, sorry, I2Z for spin 2, and this 2-spin order term 2IZSZ with the product of the polarizations. And I think I mentioned last week that you have these 2 in front of 2IZSZ, oh, sorry, I1Z, I2Z. This factor 2 in front is a normalization factor. I wouldn't be able to explain it rapidly here, but this is related to having a basis to represent your density matrix that is orthonormal, I think. And that is interesting to ask this question: how much of rho k do I have in rho? So, for example, in this matrix, I would like to have a calculation that tells me 1. I have 1 IZ in this density matrix. And so it means to decompose the density matrix in a sum of terms and that are all orthogonal with respect to each other, and know the coefficients AK of the operator of interest. So a very general way to do it, AK is given by this formula. As rho and rho k are Hermitian, it simplifies to this because it's equal to its adjoint. And for example, if you write this for IZ, here I've taken so the expectation value. This is more or less the expectation value to the detail of this normalization factor. So in this example, I calculate this value for IZ, taking this density matrix, and sorry, almost the density matrix. This is the density matrix for a single spin polarized along Z with polarization P. And when you calculate it, in the end, what you get is P. So in this case, using this formula gives you the polarization along Z. This works well for a single spin. It's a bit more difficult to define it for multiple spin system. But what we are interested in here today is this example. Is if I want to know how much of 2IXSZ I have in my density matrix, I will just do this calculation. This is what I will do in a minute. So in a way, you can understand this intuitively by saying, okay, this is the expectation value of rho k for density matrix rho, and it gives you some value, and you normalize it by how much of rho k you have in rho k. So this is the expectation value of rho k when the density matrix is rho k. So this is the sort of intuitive way to understand this formula. So now what I want to do is to apply, my screen doesn't move anymore, is to follow during this step, during this preparation session, I want to follow the creation of IXSZ and IYSZ. So let's go in MATLAB and copy our first part on INEPT. Okay, so now there are 2 operators that I will need. I'm going to call it 2. I cannot start a variable with 2, so I have to call it 2IXSZ. And this is equal to 2 times 4IX times SZ. The same for IY. Okay, then this, I want to get carbon here. So there's nothing that changes here, but in fact, I'm no longer interested in getting the spectrum in the end. It's not what I want to see in this case. We'll remove all this. I'm not even interested in this. So everything I need, in fact, is simply this. So this means rule one. This is this part. I want to follow what happens here, and I'm gonna chop this in 1,000 points. So 1,000 points will correspond to this delay here, and then another 1,000 points here. And now I need to create vectors where I'm going to store the the elements along time. T. Because I have m points per delay tau. So I have my vector has 2,000 times m. I do the same for this one. And I also want to follow ix and iy. So now I create a loop that goes from 1 to 2n. And I will propagate the Hamiltonian. So I have that's what I wanted to do. Again, I have to define a delta t. So it's tau divided by m minus 1, I guess. But in this case, it will not be super crucial to be precise. I define u delta t. As earlier. So this is my initiation of the loop. And here I will calculate all these terms. So this one will be the trace. I have added real as usual. The trace of this operator that I've created here. Multiplied by the density matrix, rho k. And now this is what we have seen in the slides. I have to divide it by the trace of the square of the matrix. Can I do this for all of them? For those who are used to matrix calculations, this is exactly equal to the Frobenius norm of the matrix, but to the square. So you can also use in MATLAB, you have this option norm, and if I put ix and fro, this will compute the Frobenius norm. If I add square, this is exactly equal to this term. That can be useful. Okay, so I have to copy this. Now this is ix and iy. Ix again. Here I just forgot to write t because otherwise I'm going to override the same one. Oh, so it's not t, it's I. So now that I have calculated this for rho k, I have to propagate rho k as we did earlier. And finally, I want to plot along time my different operators. I just haven't defined time. We go from 0 to 2 tau, and it has 2 times m points.
As George pointed out, I think your for loop needs the n to be switched to m.
Thank you. I just missed one thing here. So I'm propagating all this, and I have only 3 evolutions. At some point, I have to apply this pulse. So if I want to include this, I can say once I'm in the middle, so the middle of this loop is when I is equal to m. Now, in addition to this, I'm also going to write the effect of the pulse. And so I'm going to define it here, maybe simply here. H, I call it H pulse, will be pi over 2, and it's acting, no, pi, not pi over 2, along x for both spins. And I can directly define UP, in fact, with a exponential matrix. Yes, I have everything. So this means that the loop corresponds to the full evolution between the first pulse and the last pulse. But in the middle, we have a pulse. And I detect that I'm in the middle by checking if I is equal to m, then you apply the pulse. Okay, so let's run the code.
I believe there might be a problem also with the polarization. I think you were on carbon 12.
Yeah, am I? Yes, thank you. So I did a mistake. I don't have the same length for my vectors. Why is that? So let's have a look at the length of the vectors. We have, this is a very typical problem, so it's good practice to solve it. We have 2000 points in this one. This now we want to look at this one. IX as Z, 2000 points as well. I wonder, maybe I just, for simplicity, I write it like this. So no, so here we have a big, oh yes, of course. I wrote IX at IXT that I wanted to plot, because IX was the was an angular momentum operator. IXT is a vector where I have saved the expectation values of IX. So now I can run this again, and I still have a problem. Trigonometry, yeah. Okay, so let's check.
Is it that you're missing a T in this plot?
Yeah, between
Yeah, exactly.
Yeah.
That's why it tells me that it has to be pairs. Thank you. So what we see here is quite messy. Let's check the so this is blue, red, orange, or yellow, and purple. So blue is IX and Z. orange is IYSZ, and these the purple and yellow are X and IX and IY. So instead of so we see oscillation, so the two-spin order terms increases, and the one-spin order decreases. A convenient way to see it is to take this value so now I'm looking at the sum of these two terms as and you will see it's a bit more convenient, and I have to add the point here because I'm doing an operation element by element, and I'm going to do the same here. Okay, plot this. Yeah. So now you see this is more convenient way to see it. This is the one spin order, and this is the two spin order. And I've checked before the session today. If I take the sum of all of them, it is conserved. So here I have the sum of the four terms, the sum of the square of the four terms, and then I take the square root. If I run this, you see that it is stable here. So this is a way to monitor the creation of this two spin order term, and you see at tau, at 2 times tau, you are exactly at the maximum. So this is the way you transfer. So you can then play with tau and see why it wouldn't work if you were to choose another value. Of course, if you stop here, you haven't created that much. But it's not a full analysis of the reason why. Of course, it's better to do it analytically, but for cases where you cannot do analytical calculation, of course, you can follow the terms that are created in your density matrix using this strategy.